Jai Jirendra, Namaste and welcome to my channel. Today we are going to solve the 59th question of the problem solving series and the third question of recursion. The difficulty level for this question is medium and this question has been asked in Amazon, Microsoft, Tesco and Walmart. Perfect sum problem. That means count the number of subsequences whose sum is k. So we are given an array, the number of elements in the array n and the sum. Now we need to return, you can see in this example, the number of subsequences whose sum is k or 10 here. For example, here if you can see, sum of 5 to 3 is 10, sum of 2 and 8 is 10, and there is one more 10 itself. So there are 3 subsequences whose sum is 10. Okay, so we will return 3. So we need to find these subsequences and add it and give the count of the number of subsequences whose sum is k. So in the first two problems of recursion, firstly we have found all the sum of different subsets. Okay, so we have written all the possible sum of the subsets in an array. In the second question we have found the power set of a array, and in the third question we are finding the count of sum that is given in an array. Okay, the count of subsequences whose sum is k. Perfect sum problem. So now how do we solve this? Using of course we are discussing recursion. We will be using recursion to solve this problem. So how we will approach it? I have already discussed there are 3 steps to solve a recursive problem. We need to find the base case, we need to find the relation between the problem and the sub-problem, and we need to generalize it. So what would be the intuition? Like how do you solve it? Like in previously we have we can find all the subsets, okay, possible subsets, and then again if we have all the possible subsets, we can have we can check whether their sum is 10 or not. Okay, so that would be like already it is exponential, and then again we will see, okay, the sum is 10 or not for all the power set different. So that would be a very big brute force solution, right? So how can we approach this solution? If we can find the sum of all the counts of the subsequences, right? But we need to find, so we will see once we find the sum of all the subsequent all the subsets, we need to again count every time, okay, whose sum is 10 or not. So both ways it won't be a very good idea, right? But the basic approach that we have chosen to solve both the problems was, whenever we are choosing an element, either we are choosing it and we are not choosing it, right? So when we had an array where we are returning the sum of all the subsequences, we were taking it or not taking it. Okay, here in power set we were backtracking. So let's discuss this problem. Okay, so those who have not seen 57th and 58th question, please go and check it. Otherwise, let's discuss this problem, how we will solve it. Okay, so I'll draw the recursive stack later on. I'll just tell you the approach. So say when this element, whatever we get here, 5, if we take this and think that it can give us the count, okay, so we can take this 5, and the next step would be, we won't take this 5 and our sum would be 0. If we take this 5, our sum would be 5. Now we take this 2 here, so 5 and 2 will be there, and if we don't take, then only 5 will be there. So if you travel to the left side, if you keep on taking it 5, 2 and 3, now 5, 2 and 3 we see the sum is 10. Once we get, so we have the sum 10 already. Okay, so again we have option of choosing 10, 6 and 8. Okay, so once we travel all the elements, then only we can finalize. Okay, so 5 to 3 is a subset whose sum is 10, but if we don't include this 10, 6, 8, that means it would go every time to the left side where we don't pick it. Okay, so we will use again the pick and not pick logic. Okay, So I'll just code this, and then I'll draw the recursive stack, and then you'll understand. Okay. So we will have a current sum is equal to 0 and index is equal to 0. Okay. And then we will have a int count equal to say count sum, and then we will pass our index and array and sum and current sum. Okay. We'll pass this, and then we will return count. Now we will make this count sum a recursive problem function, and we will solve this count sum. So int count sum, inside this count sum we have index we have passed as 0 and current sum we have passed as 0. So int index, int array, int n, int sum, whatever the sum that is given, and int current sum. Okay, current sum. Now you see the approach. What we will do, what would be the base case? So when we are traveling here, we are choosing and not choosing. When will we stop? When the index cross becomes like, if we start from 0 and this is n minus 1. So from 0 we'll go to 1, then 2, then 3. We'll keep on moving forward and decide we'll take or not take. But when the index will cross n minus 1, that means when the index will become n. So if index equal to this index equal to n, so when we will increment it, then it will be our base condition. So when we will reach to the base condition, when this will go here, we will see, okay, if the sum whatever is given, if it is equal to the new sum, this will change whenever we pick the element. Okay, when we will add it. Okay, this is array like this. Okay, if sum is equal to current sum, we return 1, otherwise we return 0. Okay, because we don't count it. Now either we pick or we not pick, and in both the cases when we sum it, all the situations, then we will get the count of all the subsequences, because this one will be returned only when the sum is equal to current sum. You will understand. So int pick is equal to count sum index plus 1, array we have passed, n we have passed, sum we have passed, and this current sum we will increase it to, so this current sum before this we will increase it by array of the index. Okay, so this 5 will be included. So initially the current sum would be 0, but we have increased the current sum to 5. That means we have picked the first 0th element and we pass this current sum. So we have picked it. Now we will, once we have picked it, now what we'll do, we'll again unpick it. So we will just remove it, kind of backtracking it. So we remove this array of index, and then we have int not pick, and we call this count sum, and we pass index though it will increase, array n sum current sum. Okay, and then we will return pick plus not pick. Okay, pick plus not pick, pick plus not pick. So the summation of this will give us the solution. Now how this will solve it, right? So you'll understand. I'll draw the recursive stack, and then you will understand the time complexity for this is exponential, because we are picking it and we are not picking it, or in the both cases we have a choice, and this choice will be towards till we reach the end part for all these things. Okay, so you'll understand. Where should I draw a stack space? Maybe towards the example. Okay. So if I remove this part, okay. Just give a basic idea. So for this example only, so we have 5, 2, 3. Okay, we pick 5. Okay, pick and not pick, not pick. Okay, so when we have picked it, so our index is here. Okay, and we have picked it in the initially, so the sum is 5. Now here we have not picked it, the sum is 0. Now once we have picked 5, we have the option of picking the second element or not. Okay, if we pick it, then 5, 2, 3. So here this is, we have picked 2 and we have not picked 2. Okay, so if we have picked it, the sum is 7. If we have not picked this, our sum is still 5. There are other elements also. Okay, so if assuming the array is only 5, 2, 3 and the sum is 10. Okay, so in that case we have only option one subset whose sum is, so the count would be 1. Okay, so we have only 3 elements assuming, and now we have picked it, the 3 we have picked it, so this one becomes 5, 2, 3 and the sum becomes 10. And here we have not picked it, so 5, 2, 3, the third one, sum remains 7 only. Okay, here in this case 2 was not picked and then we pick 3, so the sum becomes 8. Okay, and here we have not picked 2 and 3 as well, so the sum is still 5. Okay, so this is there. Now here can we move ahead? So if we move ahead, our index was here 0. Here index becomes 1, here index becomes 2, here index becomes 3, and here index becomes 4, which is greater than the size of the element. Okay, so once the index becomes 4, we check, okay, whatever the sum we had, is it what we need? So if that is true, we return 1. So this will return 1 here. Okay, this part, and then here this returns 1, so this will go here, this will return 1 here. Here this one 7, this goes here, 7 is not equal to 10, so it will come into this condition, return 0. So this will return 0. So 1 plus 0, this would be 1. Here 5, 2, 3, everything 8, 5, everything will return 0, 0. So this whole thing would be returning 0, 1 plus 0, this 5, 2, 3, this will be returning 1. And in this case, when we have not taken 5, so 5, 2, 3, we have not taken 5, we take 2, and then here we take 3, here we don't take 5, 2 as well, and we take 3 and we don't take anything, so 0, 3, 2 and 3. So all this, in all the cases, whenever the index will reach to n, there will be no such value which satisfies this. So everything will return 0. So once this is done, everything is done, at the top, this part at the end, for the first call, we will have the sum of this one and this one. So 1 plus 0, it is 1. If you would have included this 10, 6, 8, so here there would have been option that we only pick 10, we only pick 2 and 8. So those would have returned 1. And when it goes to the top, that would add up, and then the sum would have become 3 for this case. So this would be the recursive stack. Okay. So since we will have recursive stack, so the space complexity would also be 2 to the power n. So I hope the explanation is clear. So this time complexity has to be improved. and we can improve the time complexity of recursive solutions using extra space and using dynamic programming logic. So that we will discuss when we will discuss dynamic programming. For now, this is the recursive solution. So also I would like to tell more, there could be variation of this problem. So here it's given count subsequence with sum is k. In the question, in the interview, they might ask return all the subsequences whose sum is k. So here, for example, this one here you would have to return say 5, 2, 3 and 10 and 2, 8. So the answer could have been like this: 5, 2, 3, return a vector like this, 2, 8 and 10. So they might ask to return this vector as well, right? So in that case, what changes you would have made? So you might have passed here in this function, you might have passed another 2D vector and v and say ds single vector and 2D vector, and here when you would have seen that okay, when the sum is equal to current sum, instead of returning 1, what you would have done, you would have added you would have added this ds into this vector. Okay, you would have pushed the vector into the 2D vector, and the vector would have you would have changed the vector here, like the sum you are changing, you would have pushed the element, and then you have you would have popped the element from the vector. So the ds would have all the solutions here: 5, 2, 3, 2, 8 and 10, all these things, and when the sum would have become 10, so for example this one, you would have this subset. So when you reach here, the sum is equal to current sum, so this ds would have contained this subset, and you could have added this to the 2D vector and you could have returned it. So you can try this this variation yourself, and for this question, the link to the question has been given in the description. Please try it yourself and then come to my code walkthrough section to verify it. Okay, thank you. Here is the code walkthrough of the 59th question in the Geeks for Geeks platform, perfect sum problem. You can see this is the same example. N is equal to 6, 5, 2, 3, 10, 6, 8, and the sum is 10. So we have this output as 3, where we have these 3 subsequences whose sum is 10. So we return the count of the subsequences. So here in this example, you can see that we have taken a vector named dp. Why have we taken it? Because we have done this using dynamic programming. Okay, so let me explain you what change we have made. So what we have done the same thing. We have this perfect sum and we have passed this index as 0. You can see over here, and the sum as the current sum as 0. This is the current sum. We have used the same logic, and the sum as this sum, and the dp vector we have passed. Just forget this dp vector for once. Okay, so we were asked that if the answer is large, if the count is big, so we need to return the modulo of we need to have a mod as 10 to the power 9 plus 7. So we have this mod, so we'll use it as we'll mod the answer to this value. So now what we have done, we have this index array and current sum and sum. Okay, so you see this is the same base case that we have discussed. If index crosses the size of the array, then we check whether the current sum has become equal to sum or not. If it has become equal, then we return 1, otherwise we return 0. Now you see we have this pick value, int pick equal to 0 is fine if current sum is plus array of index is less than equal to sum. If you would have ignored this, then also it would not have been problem, because if it is greater than this, will when this condition comes here, it would not return 1. Okay, so when it is equal, then only it would return. So that is same thing. So int pick, so if int pick is equal to, here we have added the index, increased the index, array is same, n is same, and we have incremented current sum as current sum plus array of index, and then sum is there, and then we have used this mod value because it should not cross the value here. The count should not cross, or big value, big when the elements are, when the array is very big. So at that position we have done this percentage mod, and if we don't pick it, we increase the index, but our current sum remains same. Okay, we don't select that element from as sum for the array. Okay, and once we have done this pick and not pick, then we return pick plus not pick. Here we have given this percentage mod. Now why we have used this dp space? So because we are calculating the one thing over again the other thing, there is a overlapping sub problem. Okay, so to reduce this overlapping sub problem, whenever we have already calculated a value, so we can directly check that value over here. So when this is calculated, when I'll teach dp, you'll understand this. So here, to avoid that redundant thing, we get the value from the dp table itself. Okay, the basic logic is same. So if I remove this logic here, say if I remove this dp, so I'll show you. If I submit this should pass. Okay, so this has been passed, this has passed here, all the test cases have passed. But if I don't use this dp logic, say if I comment this out, if I don't have anything dp here, and here also I remove this, now this is same, right? We remove this, and directly we remove this condition as well. And pick, and here dp is to be replaced here also. And it not pick, and this one has to be removed again. Okay, so this is the what we have discussed. So if I submit this, if I compile and run it, so compilation error, what error? Okay, dp we have not passed, right? So we need to remove this, and I compile and run this. You see the output is same, right? So if I submit this, I'll get a TLE, time limit exceeded, for the next 20 test cases. Only 1000 test case would pass, the other 20 will not pass, because it takes extra time, since it's a recursive solution. What we expect a time complexity of order n square. So that's why we need this dp. Okay, now if we submit this using dp, we will get all the solution passed. Okay, I hope the explanation is clear. See you all soon in the next video, where I am explaining the 68th question of the problem solving series and the 4th and the last question of recursion in this playlist. Jai Jinendra.